Okay, in this video, I'm going to show how I said the magnet is feeding in from both directions. Like a turnbuckle, you've got a left-hand thread and a right-hand thread. That's why they both rotate in the same direction, but they screw towards each other. It's a one-way feed for both sides coming into the magnet, and they meet in the middle. So it's like a corkscrew, a double corkscrew, left-handed threaded corkscrew and a right-handed threaded corkscrew. They meet in the middle, okay? What this video I'm going to show you is how I propose that when they meet, why they stop in the middle, why the magnetic field seems to dissipate in the middle, and why they both rotate in the same directions, but they cancel each other out in the middle. That's what this video, I hopefully will show you my explanation of that part of my theory, okay? So we'll move on. Okay, in my last video, I showed how the corkscrewing and the linear feed towards each other of a magnet, it's got to be those two motions that cause a Hall sensor to be able to pick up which is north and which is south. I hope you understand that. It's the corkscrewing. They're both rotating in the same direction, but they're corkscrewing left hand from the north and right hand from the south. That's why no matter how you apply the rotation of a pole to a Hall sensor, it always knows which one you're applying. Like I said, it depends on which side of the sensor you're on, but when these are wired right, the north will always show a north no matter how you apply the rotation, and south will show a south no matter how you apply the rotation. Because it's a corkscrew. It's not a singular rotation, it's not a singular lateral feed, it's both, corkscrew. So that's what I did in my last video, was showed those two motions are what magnets are doing, and they're coming towards each other, or they wouldn't do what they do with a Hall sensor, and you wouldn't have feed on both ends always pulling to the end like that. They're both coming in. That's why that steel ball is drawn in from both sides equally. Okay. On this video, what I'm going to do is prove to you that the corkscrew is happening and is coming towards each other, and that's why the determination of what is north and south on a Hall sensor is because of the two motions. So what we're going to do, I've got a 12-volt battery from a lawn tractor. It's 275 cold cranking amps. You know, not a big thing, but it's pretty cool. I've got my homemade Gauss meter and my voltmeter. I've got my pole identifier. I'm going to put the rotator out of the way for now. Rotation demonstration. I've got this is a hardened piece of high carbon steel that I can magnetize and demagnetize to show you this demonstration. What I have here are two little coils. There's a little piece of PVC inside each one holding the wires where I want it. They're wound the same number of times, I think 9 times, but one is wound clockwise. This one says clockwise. It's wound going that way, clockwise. And it doesn't matter which way I turn these, they're always going to be what they are. Clockwise, clockwise. So no matter which way I turn it, it's always going to be a clockwise rotation of the magnetic field through the wire. Now this one is counterclockwise, okay? It goes the other way, and it's the same thing. No matter which way I turn it, it's still counterclockwise, okay? It doesn't switch. These don't switch. So what we're going to do, first of all, and I've got my transformer here. This is just a dimmer switch I put on for a later experiment in my next video. My transformer I use to demagnetize the magnet. Let me demagnetize it. I'll show you it shows no poles. The Gauss meter here will show very little reading, 0.10, 0.09, 0.04, very little reading, but I'm going to change that momentarily. So I'm going to take the clockwise coil, rotating this way, and I'm going to put what I've got painted is south. So I put the south end into the clockwise coil. Now I'm going to energize it a couple of times and magnetize this piece of steel. Now it's magnetized, and it should show a north and a south, and this should be negative on the meter, and this should be positive, because this sensor is the same thing as this. Just we're on this end, just like that, okay? If I go back here, it'll switch. If I go back here, it'll switch to negative, okay? Just depends on which side you're on. Anyway, so we've magnetized that with a clockwise coil going around that way. Says that is south, that is north. So we corkscrewed it, and that's how this knows which is south or north. And we'll get to later how come the north is pulling back even though I shot the current one direction through it. So now I'm going to demagnetize it. Show you that there's no poles, very little Gauss, 102. And what I'm going to do this time, take the same clockwise coil. I'm going to put the red to the left, the north to the left, okay? And I'm going to energize it and show you what this does. So we had it in there this way. This should be reversed, or south and north, or south and north. It's not color-coded anymore. So it depends on which way I put this in there, but the incoming side of the clockwise is always a south. So let me show you what we just did. With the magnet in there like that, with the clockwise coil, the south was to the left, the north to the right. It color-coded just perfect. But when I flip the magnet, or the color codes, now the red shows the south and the blue shows the north. So the magnet magnetized the same, it's just I flipped the colors, okay? That makes sense if you're with me. It's rotating to the right, so it always says that is the south. That's what this picks up. Which way is that corkscrewing? See, it's backwards because I flipped the colors. Now we're going to do something else. Let me demagnetize it. Show you, once again, we have no poles. Very little reading, 0.07, 0.05. Now we're going to put the clockwise coil away, and we're going to use the counterclockwise coil, okay? So this time, I'll put the south, the blue to the left, the red to the right, and we're going to energize it. Get it out of there. Now let's see what it did. We had blue to the left, red to the right, and we're backwards. Imagine that. Let me show you here now. So on this, the clockwise coil, the blue to the left came out south. On the counterclockwise coil, the blue to the left came out north. We just reversed our color coding. What I'm showing you is the clockwise will always be the south pole where the current went in, always. And the counterclockwise coil, and I'm going to show you now, we'll do the other way with the magnet in it on the clockwise or counterclockwise. Demagnetize, no pole, very little reading, so it's demagnetized. Now we're going to put it in the counterclockwise reverse. We'll put the red to the left, okay? The red color to the left, energize it. So this time, well, let me show you what it is. Now it shows the blue is the south and the red is the north because I energized it going the other way, but counterclockwise, okay? I corkscrewed it backwards. That's why it came out right. So if you noticed, a while ago, it came out wrong, okay? With the counterclockwise coil, it said the blue was north and the red was south. When I flip this around, now it's right because the north is the same either way on the counterclockwise, and the south is the same either way on clockwise. So I hope you get that. The corkscrew action that these two coils do is what determines south or north for a pole finder or a hall sensor in any application of device. It's just that the clockwise coil, the south is always the incoming current. Counterclockwise coil, the north is the incoming current because of direction of corkscrew, okay? Leave that there a minute if you want to look it over. That's what we did. All I did was decolor code it, okay? Didn't have to repaint it, I just had to flip it. But this one will show a north always on the incoming side. This one will show a south always on the incoming side because of the direction of the corkscrew. And we'll move on. In case anybody was wondering, I didn't show because it's really not important so much. When I do magnetize this piece of iron with the battery here, it does have a Gauss number after, if you see, like it'll be 1.45 or something on the north, 1.35, and 9.97 on the south. Every time I do it, it varies how much Gauss it shows because of how long I left it on there and how many times I touch it maybe. So it varies. It's never the same every time. You know, I can do it in the same coil, in the same orientation 3 or 4 times, and it'll always have a little bit different Gauss. So that's why I don't put the numbers in, because it's really not that important. The main thing was the direction of the corkscrew as far as what the pole finder and the plus and minus on the north, plus on the south, minus on the north, plus on the south. That's the main thing about the corkscrewing, not so much the numbers, okay? It does magnetize it up to like 1.4, pretty good, because it will hold, you know, pretty good sized steel ball. It will hold that 1-inch ball. So anyway, I just want to throw that in there in case anybody said, well, did it actually magnetize them? It does, but it varies, okay? Depending on how long I touched it to the battery. And I could make it the same every time, but I'm not so much interested in the amount of Gauss as I was the direction of the corkscrewing towards each other. Okay. Okay, let's say these are the atoms in the center of our unmagnetized magnet here. It's just a magnet that's not been magnetized, you know, a piece of neodymium or hardened steel, high carbon steel. So it's not magnetized yet, so our atoms are, you know, just kind of laying there. This is too organized probably, but you get the idea here. They're just mixed matched or whatever. And they're spherical, more like this, you know, you've got your electron function going on. But it's probably more, each atom's more spherical, and they're just stacked against each other in particular ways. But I'm going to show, what I want to show with this is how this turns into, right in the middle of the magnet, where they contradict each other for when the Fibonacci swirls coming in, even though they're rotating in the same direction, they actually do cancel each other out. So now we're going to move the atoms after we've magnetized them, and we'll do that. Okay, we're magnetized now, and I didn't have any red paper, so I'm using orange here. It's not quite red, but you get the idea. In the center of our magnet, they're next to each other, the south Fibonacci coming in this way over the top to us, the north going in this way over the top to us. But now I want to show you they're not lined up like that. Remember, our domains are stacked. So now I'm going to show you what it looks like when the magnetic field of the rotation of the Fibonacci connects these to each other instead of a straight motion like centripetal, like this with no magnetization. Once it magnetizes, they get into the corkscrew. The corkscrews coming towards each other, and I'm going to show you that. This is kind of a poor example, but you notice now they're not straight. This one's coming in, rotating this way, one atom stacking against the other. These are our domains. But remember, in here, there's millions of domains lined up against each other, each swirling, and they're, you know, just paired up, swirled. The atoms aren't swirling. It's the electron functions of the dielectric being passed. But it's not passing straight through, it's passing in a corkscrew, okay? That is the magnetic field. So as they corkscrew, you have to see this three-dimensionally, and I'm gonna try and get an animation for it. Maybe I get it or not. You'll see it next, or before this. But they're corkscrewing towards each other. I'm just trying to show this how the atoms are, they're not just passing the dielectric straight through or straight in, centripetally, normal gravitationally speed. Now they've been corkscrewed towards each other. So they're stacked in a Fibonacci swirl, okay, towards each other. And we'll move on to showing you a little more. Okay, this is just going to be another analogy demonstration of how the latticing domains of a magnet line up, even though it's feeding in from both sides. They're corkscrewing left hand and right hand towards each other, but they're rotating in the same direction, like I've showed with my coils and everything else. This deck's black. I didn't have blue. And this deck is red, of course. And we're going to show, I can't do these at the same time. I have to do them one at a time, or I'm not a I'm not a card magician. So anyway, we're going to spread these out. We're going to spread these out and show that this is just the atoms of our neodymium or whatever material before it's magnetized, steel, whatever. So it's just laying there. Then we hit it with an electric current. And they lattice. But they don't lattice straight, they lattice in that corkscrew, okay? So that's the south came in. At the same time that happens, then we get the north coming in. Let me do this side. So when that happens, then the north comes in and does its thing. So I can't do them at the same time. So when they hit each other, right in the middle of the magnet, these two oppose. I probably can't get them to stand, but they oppose each other, okay? You know, they're opposing. They're actually swirled, so they're not lined up straight. They're at an angle. They're at angles to each other. They're in the same direction, but this one's pushing his corkscrew that way, and this one's pushing the corkscrew that way, and they hit each other. But there's hundreds of these lined up. All these domains are lined up, stacked next to each other, like I showed you with the animation or some of the other demonstrations. So that's why they stop each other. They hit in the middle. This one's corkscrewing in the same direction, this one the same direction, but when they hit, they can't push each other out of the way. And I'll show you either more experiments or demonstrations to show that if I haven't already. And we'll move on. I want to show one more thing is that as our lattice is there, you have to remember it's 360 degrees around the whole center of the magnet that they're slammed together like this. It's the electron functions. It's not the atoms twisted. It's the dielectric moving from atom to atom. And when these move in this way and these move in this way, they get locked up. They get in the bind in the middle. But you got to remember, they're stacked against each other all the way around the magnet, no matter what shape it is. See what I mean? They're stacked all the way to the center, all the way out to the edges. The electron functions are leaned in towards each other. They're hitting, not straight on, but at angles, which basically is the same thing, but they can only push so far. And the other demonstrations are the ones I'm going to show you, will show you or get your mind around that more. And we'll move on. Okay, before I set this demonstration up, or this little prop analogy, I want to show you what it is before I put it together so you can see what it's going to do. Here's our magnet, and remember our turnbuckle. Even though they're both turning in the same direction, they thread towards each other because the north is a left-hand thread and the south is a right-hand thread, according to this, because if I turn the south towards me, it goes in. If I turn the north towards me, it goes in. So we know they're both feeding in, but they're rotating in the same direction, but they're corkscrewing towards each other. Left-hand thread, right-hand thread. So this is going to represent our domains or lattice of atoms inside the magnet, and they should be, you know, pitched, angled kind of towards each other, but since it's a three-dimensional thing, I can't do it with this without just going two-dimensional. I'm going to mount this here in a minute, and then I'm going to mount these up here. And what I have, if you see, the north is corkscrewing towards us over the top, but it's coming in this way, over the top towards us. This one's coming over the top towards us, but they're both going towards each other, if you see that. When I get this mounted in here, what I'm going to show is one underneath and one on top as they corkscrew to show you what it does in the middle of the magnet where the two Fibonacci screws meet each other, what it's doing to what each side's trying to do to the other and why it conflicts. And it goes back to regular gravitational feed right where these two meet to a certain extent out depending on the size and shape of the magnet. So let me put this together and we'll go back or come back to it and I'll show you how this works and we'll do that. Okay, before I mount the centerpiece in there, I want to show you that they're both going to corkscrew over the top towards us. They're going the same direction, but they're corkscrewing towards each other. I mean, they're not moving towards each other, but you see how the threads are moving towards each other. Well, they're coming this way, but this one's moving that way and that one's moving that way. Okay, so I want you to see that before I mount this more permanent on this spring, so you can see the action that happens when they interact with each other. So let me mount that on the spring and I'll show you. Mount this on the spring, and I'm going to put it right between them where they're opposing sides of this, where our atoms in the center of the magnet meet, from the corkscrewing Fibonacci this way and the corkscrewing Fibonacci that way, but they're in the same direction of rotation. Okay, let me mount this and we'll come right back. Okay, on this demonstration, I've got both corkscrews on top of our double latticed atoms. I mean, you got your red side, your blue side, they're separate, but they're on one piece of paper here because they're interlocked, coming this way, or coming this way with the red and this way with the blue. But when they try and counteract each other, even when they're both on top, they're trying to spin it down, see? They're trying to push down. But these atoms are locked in with other atoms that are stacked against them in that swirl. They're all stacked together. The domains is one after the other. You know, the domains are one atom after the other, or one molecule, but there's also another layer of molecules, another layer, another layer, another layer. So you can't twist all the layers in one direction. It's trying to push them both up on this side, down on this side, and it cannot do that to the atoms in the material. They will not move like that. And furthermore, if I put one underneath and one on top, then it tries to twist it this way, and it can't do that either. You see that? It's trying to twist it this way. It cannot do that either because the atoms or molecules will not let it twist this way or this way. So that's why they contradict each other. That's why they cancel. It wants to twist. The atoms inside the magnet cannot do that. They cannot change places. So this gets stuck. The accelerated dielectric gets stuck. So it hits, and that's the end of it. These two are stuck against each other in a freeze frame of regular gravitational speed of the dielectric gets slowed down because it cannot twist them. Can't twist it that way, and it can't twist it that way. I hope you see that, and we'll move on. Okay, I'm holding the phone because I kind of have to on this deal. You see this fan, just 4 blades, and they're all turned kind of like my hand, you know, in that direction. And we're going to show this one at a time, or just one fan, but imagine, if you will, there's 2 fans, and the other one's just like that one, but facing that way, and it's rotating in the same direction, but the blades are turned opposite, so they're both blowing towards each other, okay? Magnetic field. And this one's rotating that way, so let's say that's the north. The south will be coming in this way, rotating the same way, but its blades are turned different, so it's rotating that way, but it's blowing towards that one, and that one's blowing this way. The point of this is, I want you to notice, as you look here, you see between the blades, you know, there's a little bit of gap there. There's a motor you can't see real well, but watch when it's rotating. Watch what you see. Now, it's not so much the camera frame that's showing the blades going around this way, but notice how in the middle it's always a curved angle. You don't see the blades together over here. No matter where I go, that dark spot's on this side. You see it? So they're kind of stacking, if you see what I'm saying. I go down and bring it up on top. That's always opposite from where your point of view is. If I come up here, it still kind of stays to the right or to the left. So anyway, imagine 2 of these pointing towards each other, stacking their atoms and their lattice of magnetic domains coming towards each other in the same rotation. So I want to show you that. Just imagine 2 of these facing each other, blowing towards each other, but they're rotating in the same direction. One more view. I'll even shut it off, let you kind of get an idea. You still see that solidness on that side. But when it stopped, you can see between them everywhere. See? You see between them there, but you don't here because of the angle at which it's coming across with the next one. The stacking of the domains coming in this way from the north and this way from the south are going to be opposing each other in that stacking kind of swirling Fibonacci situation. And we'll move on. Let's say this is our magnet, and it's just, 7 atoms round and 5 atoms long, or what, molecules or whatever. But it's getting dielectric. It's not magnetized yet. It's just a piece of neodymium or a piece of steel. It's just getting regular dielectric gravitational feed holding those atoms together. Okay? Hang with me. That's an electric current in the background there, getting ready to energize this with a coil. And my next video will show that. So when the electric current comes in, it's going to come in with the Fibonacci swirl with the electric current. If the coil's turned that way, then south is this side, and the north will be this side. But it's weird how this happens, and I'm going to show you in my next video how a coil actually works when it magnetizes anything, whatever is magnetic material. So it looks like it would magnetize like that with the swirl all the way through. But what happens when there's flyback? When the flyback happens, when you magnetize, it comes back in. And it's already spun up. The ether's already spun up. But when it comes back in, it looks like it would do that. They would contradict each other in opposite spins, if you will. But that's not what happens. And I'm going to show you here in a minute. And like I said, my next video will explain this perfectly. But this is not what happens. It looks like this is what should happen, but it doesn't. And we're going to move on now to show you what does happen, what I've found out, and it'll be in my next video of why. So electric current came in. When the flyback comes in, it does that. It's already spun up in that same direction. So when it's spinning and it comes back in the other direction, that's what you end up with. They're contradicting each other, but they're spinning in the same direction. It's weird, but that's how I found out it works. Once it comes back in, the flyback of the ether, to meet itself halfway through the magnet, it's already spun up. That's the only way you can magnetize. You have to spin that ether up, and when it comes back in on the flyback, that's what it does. Now let it run one more time. Electric current came in, the flyback came back. And it does this as soon as you hit it with the electric current. The flyback is instantaneous. I also found that out. So this is what we see the atom, just a bunch of, or the magnet, just a bunch of atoms, the south and north, just a piece of neodymium or a piece of steel magnetized. But what it's actually doing, the domains are doing what you see on the right. All of them are doing it like on the left, but on the right is what each domain is doing. The reds are contradicting the blues, the south is contradicting the north. They're corkscrewing towards each other, but they're rotating in the same direction. And that's just how it winds up. And like I said, my next video will show that.